that they individually have quite complex things to do, but you can give one command and make them all turn or halt or whatever.
And each soldier has planted deep down in his consciousness something that has been drilled to do.
Exactly, that what he wants, what he has to do in that sequence.
Escort! For the colour!
Just carrying the military analogy a little bit farther, if I give you a command, shoot at a target, as a trench soldier, you'd know exactly what to do.
Right, yes. I mean, it just happens by an amazing coincidence I have a rifle here, and I think, let me just see if I know what you mean. You can divide the action of simple command, like shoot, into three sort of routines. It's load, aim, and fire, and they're all of them quite complicated. Loading means opening that, stick a bullet in there, close it up again. With any luck, it's loaded. Aiming means lining up, yes, clear, there's nothing in it, but let's not take any chances. Lining up the target with the two sights on the front and back of the gun, looking through and making sure that it's all lined up. And then the firing part is another muscular activity, which is pulling the trigger finger like that. And when you're satisfied that everything's lined up properly, fire. And those are three quite complicated routines, all embodied in one very simple word, shoot at the target.
In computer language, we call them subroutines, right, parts of a main routine. And perhaps I can show you, if you pass me this rather large book of steam organ music, yeah, you'll see something of what, what we mean. If you look carefully at this, you can find two pieces of this music which are very similar. There's a piece here, yes, and there's a piece down here.
Right.
And we can think of those, they're probably just repeats of the same refrain. Well, you could take that out and take that out, and at this point you have an instruction which says play this section. You've just stored it once, and when it's played it comes back to this point on the music. We could have a command which says play refrain, and it would play the refrain here, it would play the refrain there. In other words, that was a subroutine. And by that command of saying play refrain, we've almost started to invent a computer language, even for the old steam organ.
Now, we've talked about language a lot, and I must admit to being quite confused by the diversity and number of computer languages. We've got a program running here which lists the BASIC, COBOL, Fortran, Pascal. There's an absolutely dazzling number of languages. Now, how on earth do we tell what languages they are? Presumably they're all like French, German, Spanish, and so on. How do we tell one from another? And which
using your analogy of ordinary languages, for example, in Eskimo, there's hundreds of names for snow because they want to talk a lot about snow. In Arabic, apparently, there's lots of names, lots of words to do with camels. And similarly, there's been attempts at computer languages to make programming easier and easier. And so many different attempts have been made, specialized languages, general purpose languages. We end up with this terrible confusion.
And which one are we using?
We're going to use BASIC, and that is a very popular language. It's a popular language for people to start learning how to program. And this particular machine runs in BASIC.
And most microcomputers work on BASIC, do they?
Yes, they do. Almost every microcomputer would have a BASIC. And although it's the most popular, it has certain problems with it. First of all, it's very easy to make mistakes in BASIC. And secondly, there isn't really a standard BASIC that you can use on every microcomputer. They're all in some way a little bit different.
If we wanted to use a different language on this, could we?
Yes, there's a much more professional language called Pascal, which is a much more disciplined language. It's more rigorous, and it's more difficult to make mistakes, and it's also more transportable.
But more difficult to learn?
Yes, and for a beginner it will be more difficult to learn. So that's why for a beginner, many of them start off in BASIC.
And BASIC, which is running on our microcomputer here, was originally designed to make programming easy to learn for people like me. But there are other, less common languages which have been designed for doing very special jobs. Jill Neville.
This is what engineers call a drive shaft, and you'll find one like it in most heavy vehicles and most heavy machinery. Though it's a complicated shape, full of curves and angles, with a thread top and bottom, it can be made in just 4 minutes from a plain steel bar like this one. What's more, it can be made on a general-purpose lathe, which could equally well be turning out bolts or pipe fittings. Modern lathes are, of course, very sophisticated pieces of machinery, and for some time they've been fully automated. But it's only with the growing need for flexibility that they've actually been controlled by computer. But of course, you can't just stand a computer by a lathe and expect it to turn out components. Someone's got to tell it what to do. Peter, how do you get it across to a computer that it's now in charge of a very complicated lathe?
Well, first of all, this computer, same as any other computer, needs a main program, so it can understand it's got a lathe on the other end of it. from a simple set of instructions, the spindle and chuck arrangement can be made to revolve at the required speed. The cutting tools can be made to be brought into position and cut the shape required for that particular component. The tailstock can be brought in to support the work, or from the instructions.
Well, let's go back to the computer itself. If I've got this drive shaft in my hand and I want another one, how do I tell the computer that that's what I want?
First of all, there's a set of instructions written and punched out on a paper tape, which are then stored in the memory of the computer. And the first instruction tells the machine that it's going to run in metric units. G71 means metric. M42 means a gear change.
So each of those is really a code for a rather specific process.
That's right. Each line or block is to do that. We can perhaps look a little bit further along in the program. G96 means the constant cutting speed. So it means the material is being cut at a constant rate.
So what you've got here is a very simple code unlocking a whole sequence of actions which is already stored in the memory. So, to make a drive shaft like this, you need a special language, a form of code if you like. The language may seem strange at first, but it's easy to learn. And though its applications are limited elsewhere, here on the factory floor, it's exactly the right tool for the job.